Welcome back to my YouTube channel. Today we are going to see State Board Class 10 Science 1 Chapter number 4 Effects of Electric Current Part 2. In a Part 1 already we have discussed about the electric current and its effect. Today we are going to continue further in that, and we are going to learn about the magnetic effect of electric current. The first heating effect, what we have studied in a part 1, in that already we studied that whenever there is a flow of electrical current in the electrical conductor, then there is a production of the heat around it, or it starts to get heat up. As more and more current is drawn, or the higher is the resistance, and for a longer time if the current is passed in the conductor, then it produces a heat. We had already said about that. Now in the further part of the chapter we are going to talk about the magnetic effect of electric current. Means we are going to find out, is there any relation between the electrical current and the magnetic field in or around to the conductor. And after that we are going to talk about the relation between those two, if it is there. Now the further part what we are going to see in this is a experiment performed by the Oersted, who had done work in this particular field. In the year 1820, he given a concept of electromagnetism. While performing in a laboratory, he found out that when there is a flow of electrical current in the electrical wires or the conductors, then it produces a magnetic field around it. And the direction of electric current decides the direction of a magnetic field. And this they have shown over here with these two pictures. You can see over here the two electrical circuits are there, picture A and picture B if I am labeling them. In our first picture, you can see the power supply and the direction of electric current. Whereas in a second picture, if you will see the power supply and the direction of a current, they are opposite to each other. And due to that, what happened? The deflection in the magnetic needle. You can see this one is deflecting this way, whereas this one is deflecting downward from the north. So this change or the reversal in the magnetic needle's movement is because of the electrical current's direction. So what he suggested, or what he gave in the electromagnetism, that there is a magnetic field around the conducting wires, and the direction of that magnetic field is decided by the direction of the electric current which is flowing in the conductor. Now the further part, when we see about this, then one more experimental part which we have in a practical sessions also. In this, what we have, the conducting wire through the key, through the emitter and power supply. In this, if you will see, this conducting wire is passing through the cardboard. This one is the cardboard, and the hole at the center, and the wire is passing through it. Once we switch on the power supply, we get concentric circles on the cardboard of iron filings. Means at the beginning, before switching it on the electrical circuit, we are sprinkling the iron filings on the card sheet. We just sprinkle on it, and after sprinkling on it, when we switch on the power supply and we tap this from the corner, we have to tap this card sheet, and what we are finding, that the iron filings are making a concentric circles. Concentric circles are nothing but the circles with the same center. So here you can see this, you can consider as a center, and you can see they are forming the concentric circles. You can see. But as we move away from the conductor, you will find they are rarefied. They are rarefied means the visibility of the circle is not clear as we move away from the conductor. Near to the conductor, we are having a clear circles. Why this is happening, and or from this what we can draw out, that is the near the conductor we have a strong magnetic field, and as we are moving away from the conductor, the strength of a magnetic field is reducing. So this is about the magnetic field produced around the conductor when there is a flow of electrical current in the conductor. You can see they have mentioned over here a magnetic field is produced around a straight current carrying conductor. If the current is unchanged, this magnetic field reduces as the distance from the wire increases. Therefore, the concentric circles representing the magnified lines of force are shown bigger and rarefied. As the distance from the wire increases, if the current through the wire is increased, the intensity of the magnetic field increases. So this is about the magnetic field around the conductor. Now, what will be the direction of magnetic field? How to find out that? For that, we have right hand thumb rule. Right hand thumb rule, what it says that what we have to do, the right hand palm, we have to curl the fingers around, we have to curl the fingers around the conductor, and thumb we have to stretch outward. We have to stretch the thumb outward in the direction of the electrical current. So in this picture you can see they have done that way itself. Thumb is in the direction of electrical current and the fingers are curled around the conductor. So when we keep the stretched thumb in the direction of the electrical current, then the curled fingers give the direction of the magnetic field. You can see this is the direction of the magnetic field around the conductor. And that magnetic field's direction is nothing but the same as the direction of your curled fingers. When the thumb is placed in the direction of the electrical current's direction. This is the right hand thumb rule, and this helps in finding out the direction of the magnetic field generated or produced around the conductor. Now, magnetic field around or the magnetic field produced by current through a circular loop of a conducting wire. Now here loop means this, the circular formation by the conducting wire. This is called as a loop. Now here you can see we are having this particular picture, and the direction of a magnetic field is different on both the side. You can see from here it's going like this, and from here it's going like this. Why? Because here the direction is changing. Direction of current over here, if I want to draw, in this section direction is like this, and in this section direction is downward. And that's why the direction of a magnetic field is reversed in both the situation. They are opposite to each other. From here you can see the direction is like this, and here the direction is like this, because the direction of electrical current in both the sides of the loop is different. Further, this magnetic field lines, that details already we have studied in a previous standard. Now, on the other side, when we discuss about the solenoid, solenoid means what? You might have observed that cylinders, if suppose I am taking a conducting wire, and on one particular cylinder I am taking a rounds of wire. Just see this. If I am taking a rounds of wire, means number of loops are connected together. So this loop, if it is formed on the cylinder, the non-conducting material, then it will be called as a solenoid. It will be called as a solenoid. And this particular structure, the solenoid, the number of loops are together, is also producing a magnetic field. Each individual loop is producing a magnetic field and all are in the same direction. So in that also there is a production of the magnetic field, and this will be the direction of a magnetic field. This direction of a magnetic field is very important in discussing the further phenomena what we have to study. This is about the solenoid, force affecting on current carrying conductor in a magnetic field. Now, in this particular section, force acting, just read it carefully, force acting on current carrying conductor in a magnetic field. So this is a one magnetic field and another magnetic field which will be generated around the conductor. Two magnetic fields are there. Always keep in mind when we are discussing about the force acting on current carrying conductor in a magnetic field, then two magnetic fields will be there. How? Let's see in this picture. Here, this permanent magnet, which is having its own magnetic field, and the current carrying conductor, this wire. In this, when the current starts to flow, this will also produce its magnetic field. This will also produce its magnetic field around the conductor. So this two magnetic field, if I want to number them, this first one is here and the second one what it will produce. Two magnetic fields, and the effect of that is conductors start experiencing a force on itself. Now they have shown over here, if you want to see in this picture, you can see in the schematic diagram they have given over here. See, one magnet is here, its magnetic field, and this is a conductor which carries the electrical current. When current is zero, no magnetic field, so conductor will be straight. No issue will be there, or no movement or the no force will be experienced, because if current is not there, no second magnetic field. Now here what happens when the electrical current starts to flow in the conductor, then it will produce its magnetic field, and due to that there will be a attraction between magnet and the conductor. And if we will reverse it, then there will be a repulsion. So both the possibilities are there, attraction and repulsion. It all depends on the direction of the magnetic field produced by the electrical wire or the conducting wire. Now this force, how to find out the direction of a force, what will be the force of the, or what will be the direction of the force when there is a electrical wire or the conducting wire and it's producing the magnetic field around itself. To understand that, we have a Fleming's left hand rule. What we have to do, we have to stretch the first two fingers and the thumb, and we have to arrange them in such a way like a three-dimensional axis. Three-dimensional axis means all the three fingers, the thumb, index finger and the middle finger, should be perpendicular to each other. You can see in this picture, if I want to show to you, thumb and index finger is perpendicular to each other. If index finger and the middle finger is taken, it's also perpendicular, and even this is also perpendicular. Means if I want to draw it, then this will be this way, and this will be the joint of your index finger and the thumb. This will be your middle finger, index finger and thumb. All the three will be perpendicular to each other. That way we have to arrange. Now after arranging your left hand, simultaneously you can try also. If you are arranging this in a mutual perpendiculars, the thumb, index finger and the middle finger, any two fingers you have to arrange. If you are finding the force, then the index finger and the middle finger you have to arrange. If you want to know about the direction of a magnetic field, then force and direction of a middle finger you have to arrange. Means any two, if you know third one you can find out. But the basic, this one is used to find out the force on the conductor. And to find out, we have to arrange the middle finger and the index finger. Middle finger we have to arrange in the direction of the current, and index finger we have to arrange in the direction of the magnetic field. We have to arrange it in a direction of a magnetic field, that the permanent magnet which we are using. Once we are arranging this two, then the stretched thumb will give you the direction of the force on the conductor, what it will experience once the current start flowing in the conductor. This is about Fleming's left hand rule. So in the next lecture we will discuss about the uses of all this in the electric motor and some more topics.